Hi everybody. In this video I wanted to walk us through the lab in which we're going to analyze aspirin to figure out how many milligrams of active ingredient in an aspirin tablet using spectrophotometry. Now you want to make sure you understand the basics of spectrophotometry before jumping into this lab, and you remember that spectrophotometry essentially uses light to figure out the concentration of a solution. The aspirin active ingredient is acetylsalicylic acid. And it's a colorless solution. So how can we possibly use spectrophotometry to analyze a colorless solution? Well, we're going to dye the aspirin. We're going to dye the aspirin using iron 3 chloride. There's what iron 3 chloride looks like. And our first task in this lab is to prepare 250 mils of a 0.04 molar solution of iron 3 chloride. That is the dye which we're going to be using to color the active ingredient in aspirin. Now, you remember when we studied molarity, we can calculate the number of moles of iron chloride we'll need in order to make 250 milliliters of solution. Of course, we'll need the molar mass of iron 3 chloride. Can you calculate what the mass of iron 3 chloride I must have measured out here is? This is a good time to quickly review how we should prepare a solution from a solid. Once we've calculated the amount of solute that we'll need, we should add it to a 250 milliliter volumetric flask. So here's what that looks like. I'm going to first add the solute to the volumetric flask, and I've measured out the right amount. So after adding solute, I can dilute to the mark. You notice there's only one mark on a volumetric flask, and it's for the precise volume this volumetric flask is designed to make, 250 mils. I'm going to go ahead and add distilled water until I get close to that mark, and then I'll top off the last few milliliters with a pipette, and that way I'll make sure I have exactly 0.04 molar solution, which is what this lab calls for. So that narrow neck of the flask is what allows you to measure that final volume precisely, and this way we're not adding 250 mils of water. We're adding the right amount of water in order to make the total volume of the solution be 250 mils, because the solute itself takes up some small amount of volume. So it looks like I'm right at 250, and that is the dye solution we're going to use in this lab. Next, I'm going to take a little bit of parafilm to cover up the top so I can mix this, and then make sure it's completely dissolved before transferring it into a storage container. So let's take a look at the procedure and go to the next steps. We want to take 40 mils of the dye we just prepared and set it aside in a small numbered vial. We're going to use this to do that. And the remainder of the dye is set aside for day 2. We're going to need that dye later. It goes on to explain that the active ingredient in an aspirin tablet is called acetylsalicylic acid. So sometimes when people say aspirin, they're referring to this active ingredient. We'll just abbreviate ASA. And that needs to be prepared before we can analyze it with our dye. It says to use a glass 250 milliliter Erlenmeyer flask to heat an aspirin tablet in 20 mils of 1 molar sodium hydroxide. After it's been dissolved, we're going to dilute that to a total volume of 200 mils. So let's go ahead and do steps 2 and 3. Let's see, step 2, dispense 40 mils of the dye into a small numbered vial. I've measured out 40 mils of the dye. I'm going to go ahead and put that in this small vial, and then it says to transfer the rest of it into a 250 storage flask, or to set aside the rest of it for later. So we've got one 40 mil sample of the dye, and we have another 210 mils left over here, which we're going to use later. I'm going to go ahead and put that in this storage vial, and we're going to need that a little bit later in the lab in day 2, because we not only want to dye the aspirin in our tablet, we want to dye a series of known concentrations of the active ingredient. So we'll set that aside, and we'll set this small sample of it aside as well. Next, in step 3, we want to prepare this tablet for analysis, and it says that it needs to be dissolved in 20 mils of sodium hydroxide. So So we're going to put this into a glass Erlenmeyer flask, and I've measured out 20 mils of sodium hydroxide, which is 1 molar, and it says to gently heat the solution, but if memory serves, this should dissolve without too much heating, or without any heating, if I give it just a few moments. So it looks like that's been almost completely dissolved. There is a little bit of insoluble filler, which will not dissolve, but the active ingredient is now in solution. The next step says to dilute that to a total volume of 200 mils. So I'm going to do that just by using the graduations here on the flask itself and bring that water level up to 200 mils. All of the active ingredient is now in solution, and the little specks you see floating in there are insoluble filler. So the next step in the procedure asks us to take just 5 milliliters of this and to add it to the numbered vial from step 2. In other words, the dye. Now, we're only going to take 5 mils of this, which means 5 mils out of 200, that's only 1/40th of the sample. So we're going to want to remember in our final analysis to multiply by 40 in order to account for the fact that we're only really taking 1/40th of the tablet. Now, we're going to measure out 1/40th of the tablet, in other words 5 mils, by using what is called a pipetter. Let me zoom out a little bit so you can see that. Let me go ahead and get the dye container ready. I'm going to be adding 5 mils of the active ingredient to it. You might remember using a pipette and pipetter before. This just allows us to measure a very precise volume. And I'm going to go ahead and draw up 5 mils, and then I'm going to transfer it here. Remember, the reason we're doing this is because the aspirin is colorless, and you can't analyze a colorless solution using spectrophotometry. However, when I add it to the dye, you'll see a color change occurs. Now that dark color is what we're going to be analyzing the absorbance of using spectrophotometry. And how dark or light that is going to tell us how much active ingredient. Of course, we won't be able to tell the concentration of this unless we have a standard to compare it to. You remember the principle of spectrophotometry. In order to know what concentration of aspirin this corresponds to, we need to have some known concentrations to compare it to. Let's look at a different example for just a moment to remind ourselves about the principle of this lab. In order to find out what the concentration of this particular sample is, I need a set of known concentrations to compare it to. So, for instance, if I know that this is 1 molar, this is 2 molar, 3 molar, 4 molar, and 5 molar, then I can place this somewhere along that spectrum just with the naked eye, and a spectrophotometer can do it even more precisely. Now, we have an unknown solution of our aspirin tablet, but what we need is a set of standards to compare it to. So day 2 of the procedure is about making those known concentration standards in order to compare this to. All right, let's talk about the day 2 procedure now. I've prepared a solution of acetylsalicylic acid, or ASA, which is 0.013 molar. And it says in the procedure that this has been put in burettes at lab stations. Well, here's what a burette looks like, and this is a really important bit of lab equipment that we're going to want to be familiar with. We're going to be using it in the next lab as well, and essentially it allows us to measure very, very precise volumes. On the day 2 procedure, steps 5, 6, and 7, I'm going to skip in this video because those were addressed when we learned about the basics of spectrophotometry. And essentially what we're doing in day 2 is we're making a serial dilution. This is the example that I gave before of a serial dilution of a couple of different blue solutions. Going from 1 molar to 5 molar. We want to make a serial dilution of this active ingredient, which is colorless, but that's why we're going to dye it. So step 8 says that we first need to take 40 mils of dye. We want to make sure we're using the same volume of dye, which and that's so that the difference in how dark or light the solutions are will be entirely due to the concentration of the aspirin, not due to varying amounts of dye used. And it says to add 1 ml first. Using a burette is a little bit tricky. We need to turn the stopcock here to just allow a tiny bit of the solution to go in at a time. If I turn it a half turn, essentially 1 drop goes in, which is not even a tenth of a mil. I'm going to try to get exactly 1 mil in here, so I'm going to bring the volume down from 20 to 21. And you can see that the solution is getting darker. It's not mixed yet. Let me go ahead and finish putting that 1 mil in. And these half turns allow me to get a very precise volume, and you can see now that it's dyed. However, if you look closely, you'll see that the dye has only settled at the top of the solution. I want to mix that thoroughly before I go and measure the absorbance of this solution. So I'm going to mix it just by transferring it to a different cylinder. And now it's effectively mixed. I'm going to go ahead and put that into a cuvette. We really only need a tiny sample in order to measure the absorbance. So this is solution A. I'm going to go ahead and make solutions B through E. Okay, so we have made solution A. Before we make solutions B through E, let's go ahead and measure its absorbance. I'm going to show you how these steps that we skipped earlier work. I'm going to tap here to change it from time-based mode to events with entry mode, which means it's only going to record data when I tell it to keep a data point, and the entry is going to be a number that I type in. The entry is going to be a molarity, measured, of course, in molar. And that's because I know the molarity of the solution that I'm about to put in here. It's 0.0013 molar. How did I know that concentration? Well, from the MIVI equals MFVF calculation done in the data table. Let's go ahead and measure the absorbance of this first sample. I've already calibrated the spec using this blank at 565 nanometers, so I'll put the sample in, close it up, and get that first reading. Notice when I press play now, it's going to go to the events with entry mode where the keep button appears. I'm ready to keep this first absorbance value, which you can see is 0.456 or 457. I'm going to tap keep, and it's going to prompt me now for the molarity. What was the molarity of that solution? 0.0013 molar. Of course, the second one had 2 mils from the burette, so it's going to be 0.0026. So next I would go and do the same for solution B, solution C, D, and E, each time recording a different absorbance. I'll show you what the data would look like when we're all done. I actually have data from a previous year. The students saved the file last April 10th as horses in the back, and it just turns out that this is a great example of some sample data for this lab. So let's open that up. So here's their data. Solution A had a low absorbance. Solution B, an even higher absorbance. And it makes sense because solutions C and D and E are ever more concentrated, and as they're more concentrated, they are darker, and so more light is absorbed. It looks like a linear relationship. And in step 11 in the lab, it shows you how to make a line of best fit on this graph. We select curve fit from the Analyze menu for absorbance. This looks linear to me. I'll go ahead and choose that relationship to model. You can see the correlation is pretty good. We're going to want to refer back to these numbers later in our lab in order to calculate the concentration of our unknown after we measure its absorbance. So this is a part of the video that you may want to refer back to. The M value, or that slope, and that B value are going to be used to calculate concentration from absorbance. Now we can assume that this B value is 0, since really the 0.00 should be included in this graph. If it has a concentration of 0, it would have an absorbance of 0. So really the only number we need to make note of now is the slope. So this would be a good time, so you don't have to come back to the video later, to just make a note that the slope of our line is 1,358.6. Let's keep that curve fit, and we'll look at the data table. Some of the data table you're going to need to calculate. For instance, how much water do we need to add in each case, and what is the final concentration? Here the concentration is only shown to 2 significant figures. I'm going to change that so you can see the actual values. These are the answers you should get from the MIVI equals MFVF calculation. You can ignore this column which says percent transmittance. Percent transmittance is related to absorbance. It's basically describing how much light gets through as opposed to how much light doesn't get through. But we're going to be using absorbance values in our data table. So if you look at the last column of the data table, it asks you to report absorbance. And these are the numbers that you want to put in there for solution A, B, C, D, and E. So what's left to do? Well, we still haven't measured the absorbance of the actual aspirin tablet. We've only measured the absorbance of all of our known concentrations of aspirin in solution. So we're going to take the aspirin tablet sample that we prepared earlier and measure its absorbance. We'll go ahead and take the blank out that I had in there, and we'll put the aspirin sample in there. Remember, that's only 1/40th of the tablet because we diluted it before and we only took 5 mils out of 200. And you can see that the absorbance is 0.692. Now it fluctuates a little bit, but we're going to use the 0.692 number and record that as the absorbance of the unknown. So that wraps up the procedure for this lab. And we want to set up lab journals like we've done in the past. You can see it's going to say, for the purpose and procedure, see attached page. And for the data table, you're going to want to make a data table just like the one that's shown here in the lab handout. The molarity, we've talked about how that can be calculated using MIVI equals MFVF. The final volume in each case was always 100 mils because even though I started with 40 mils of dye in each case, I always diluted up to 100. We used slightly more acetylsalicylic acid in each case, and that's why we had higher and higher absorbance values. And you should be able to reason about how much water you'd need to add in order to get a final volume of 100 in each case. A separate video will talk about the data analysis and how we can find out exactly how much active ingredient is in the aspirin. Remember, the purpose of the lab was to figure out the amount of aspirin in a tablet, and in that video I will go ahead and reveal what the real answer is once we've gone through the calculations so that we can figure out percent error. Now, you can see it also says 2019. Perhaps we'll find out that the shelf life of aspirin is actually something to be paid attention to. It does say that this is valid until October of 2020. So if our calculations are correct and we get a 0% error, then I guess we can trust that this stuff really does not degrade significantly over a year. So that's all for this video. Go ahead and set up your lab journals, set up the data table, so that in the next video we can talk about data analysis and calculations.